Okay, so in the previous video, we discussed the sampling distribution of the sample mean when the population is normally distributed. Okay, so for today, we are going to continue to discuss the example that your distribution of sample mean, what happened to the distribution of a sample mean when the population is not normally distributed. Okay, so again, just to recall back a bit, so the X here we call as population, and then the mean there we call it as a sample mean. Okay, so in the previous video we learned already how to solve the question that involve the sample mean when your population is normally distributed. Okay, so for today one, when your population is not normally distributed, what will happen and how are we going to continue with the calculation? Okay, generally the idea is also not hard. Okay, so let's have a look. When you are taking a sample from a population that is not normally distributed, then the distribution takes the characteristic of normal shape as the sample size increase. Okay, so that means when your population is not normal, it doesn't matter, because if your sample size increase, then they will also show you the characteristic of the normal distribution. So it can be shown through the diagram below. All right, so the below diagram is just for your understanding. All right, if you want to prove or whatsoever, it's quite impossible for us to prove it unless you carry out a complete survey and process for sampling distribution. But they actually realized that when they try to increase the sample size, the sample mean will look more normally distributed. Okay, when the sample size increase, although the population is not normal. So we take an example here. Let's say now your population is binomial distributed. So binomial distributed means it's not normal, all right? So when the population is not normal, when they take out a few samples according to the different sample size, so first they take the sample size n equals to 10 and they plot the graph for mean of sample. Then this is a graph you have. Okay, then after that, when they increase the size to 15, this is the graph that we have for the mean of sample, or for the graph of sample mean. And after that, when we increase again for the size of 30, and then you will see that this graph very look alike the normal distribution graph. Okay, for these two, they are not so symmetry yet. All right, but when your n hits 30, you'll see that it becomes normal. That means left and right hand side almost symmetric. Okay, all right. So this is one of the example, one of summary that it can show us. All right. Okay. So with another example, if let's say you're having Poisson, population is Poisson distributed. Again, this is not normal distribution. When they try to figure out and take the sample size according to, take the mean sample mean according to the different sample size again. Okay, so you'll see that when sample size equals to 30, then the graph that for the sample mean becomes very, very similar to the normal distribution graph. That means left and right hand side, they are almost symmetric or very close to the normal graph. Okay, all right, then the next one. How about if let's say you're having a probability density function like what we learned in chapter 3, okay? So your population original graph looks something like this, totally not normal at all, right? Okay, so when you want to take the sample from this population, okay, how will it look like? So if let's say the sample mean that you take out from the sample, right, with the small sample size, okay, the graph will look something like this. And after that, they increase the sample size a bit and see how will the graph look like. So the graph will look something like this. And again, when they try to hit sample size of 30, they realize that, again, the graph for the sample mean will look very much alike like the normal distribution. Okay? So from a lot of maybe experiment they carry out and everything, and they try to observe, okay, all the result, all the graph from different experiments, they realize that, okay lah, at n equals to 30, all right, more or less, the sample mean will look like a normal graph. All right, so from all the experiment and all the observation that they get, okay, they try to come out with this important theorem or property, or we call it as theorem. So theorem means that you can it straight away. All right, no need to prove it anymore. Okay, so all this theorem is actually get from a lot of different experiments, and they come to a conclusion. So this is a conclusion for a lot of experiments. All right. Okay, so for this important theorem, we call it as central limit theorem. So for central limit theorem, we write as CLT generally. Okay, so what does CLT means? So the summary for all the experiments that I show you above, okay, actually tell us that for non-normal population, right? For any non-normal population, okay, the sample size tends to be normally distributed when n tends to infinity. So when n tends to infinity means that when n is very large, right? When n is very large, generally it will look very similar to the normal distribution. Okay, but maybe as a reference, when n is large, so they set n greater or equals to 30, then the sample mean is approximately normal. So in short, for central limit theorem, it means that for all the non-normal population, okay, your sample mean will be normally distributed if the n is greater or equals to 30. So that's the meaning of central limit theorem. Okay. All right. So now, do you still remember that maybe in the previous video I showed you one summary, right? For this whole chapter. Okay, so this is a summary that I show you. Okay, and then for last week, we already discussed the first case where our population is normally distributed. So this is for last week. Okay, so for this week, or maybe for this video, we are going to focus on the remaining three types. So all the remaining three types here, all these are population not normal. Okay, so the population is not normal distributed. Okay, and then after that, for all the non-normal population, you will see that we actually apply the CLT. Apply CLT, apply CLT, apply CLT. Only one case that we didn't apply the CLT. What is the case? When the population is normal. Okay, so for this part, it is one of the famous questions that they like to ask in the exam. So like usually they ask you to answer a certain question about sample mean already. So they will ask you, for this particular question, do you apply central limit theorem or not? Okay, so to decide whether you want to apply central limit theorem or not, very easy. You just look at the population. If population is normal, then you do not apply central limit theorem. If the population is non-normal, then you have to apply the central limit theorem. Okay, but it is a very famous question that they would like to ask on off. Okay, after they ask you to find out the probability and everything, they will ask you whether you apply central limit theorem or not in this example. Okay, all right. So this is something that you need to know. Okay, and then if you look at detail, right, for population which is not normally distributed, for me, I separate it into three cases again. The first case is population which is continuous. So continuous means you find the probability by using the integration one in chapter 3, right? So for continuous random variable. And then after that, I separate into discrete part. So for discrete part, we have binomial and also Poisson. So the detail, we'll look at it later. All right, okay. So for now, in general, we have 4 cases. And for this video, or maybe the next video, we are going to cover the next 3 cases. Okay, and all the next 3 cases here, we apply central limit theorem actually. And also, you need to know that the population for the 3 cases here are population which is not normal. Okay, yeah? All right. Okay, so here they tell you in short, in summary, if your population has mean, okay, when you look at this mean, it doesn't mean that it must be from population. Sorry, it must be from normal distribution. No, mean, population mean, and also the population variance. Okay, no matter they are from binomial, Poisson, or continuous, or whatsoever, right? When the n is large, by central limit theorem, you can say that the sample mean is normally distributed, approximately normally distributed. If your n is larger, then the approximation will be better. So that means if your n, the sample size is large, then the sample mean, right, when you calculate the probability, it will be more accurate, okay, because it acts more like normal distribution, okay. All right, then again, when you want to calculate all the probability involving the sample mean, you still need to standardize the formula, standardize the sample mean. Okay, the whole process is more or less the same like what we learned in the previous video actually, just that you need to know how to differentiate the different population. Okay, all right, so let's start with the very first case. Okay, so for the first case, for first example that we want to discuss here is example 9. So in the bracket here, I put it as a sampling from a non-normal continuous population. Non-normal continuous population. So that means it is something like it is continuous. Okay, the variable is continuous, but it's not normally distributed. Okay, all these cases are in the exam, you have to identify out yourself. Okay, so you have to be very careful. You have to read every single word very carefully to see which case it belongs to. All right, so you can read the question first. Over a long period of time, it is found that the amount of sunshine on any day in particular town in Spain has mean 6.7 hours and also standard deviation 3.1 hours. Okay, so they are talking about the amount of sunshine. Okay, so is amount of sunshine countable or not? It's not countable. All right, because you can see it is in terms of hours, so it is quite impossible for us to calculate it. It is not countable, you cannot count it one by one. All right, so from here, you know that this is a continuous random variable, the continuous variable. All right, and then in this sentence, you didn't see any word that is related to normal. Correct or not? All right, so that means this is a non-normal continuous population. Okay, all right, then now, that means from the sentence, you only know that the population mean is equals to 6.7, and then the population variance is 3.1 squared. Okay, all right, so now, first, let us start to answer the question. Find the probability that the mean amount of sunshine. So please highlight the word mean amount of sunshine. This tells you that it belongs to the sample mean question. Okay, over a random sample of 300 days is between 6.5 to 6.8. Okay, so how can we start to do this kind of question? Okay, so first, again, the same thing happened. You see the keyword mean amount tells you that this question is from sample mean question. All right, so sample mean question, you just write out the sample mean. For our syllabus, right, it is always normally distributed one. But if you want to check in detail, right, you can check with the n. The sample size is 300 days, so the n is very large. So when the n is large, that means automatically your sample mean will be normally distributed, regardless what is your population. Okay, all right, so how to calculate the mean for mean? So exactly the same like what you did in the previous video. So the mean of the sample mean will be the same as the population mean, which is 6.7. And then for the variance of the sample mean, you have to take population variance divided by what? Divided by sample size. So your sample size is 300. Okay, so if you expand it correctly, then you should have 961 over 30,000. Okay, so this is the distribution of my sample mean. And then after that, they want us to calculate that the probability that the sample the mean amount is between 6.5 until 6.8. So the same thing happened here. You want to find the probability for 6.5 until 6.8. Okay, so first, because you know that it is normally distributed already, therefore you have to do the standardization. Okay, so how you do the standardizing? So 6.5, okay, then minus the mean, divided by standard deviation of your sample mean. So which is 961 over 30,000. Okay, then after that, I'm having this. Then the same thing happened here, 6.8 minus the mean divided the standard deviation. Okay, all right. So the remaining step will be exactly the same like what you learned previously already. So you have 1.117, then Z, then 0.559. Okay, so if you continue further by writing out the proper step and find the normal distribution table, you should get the answer which is 0.5798. Okay, so I will skip the steps here to let you try out to find out the answer from the normal table. Okay, so you can see actually the process is exactly the same like what we learned before. Just that for now, you need to check your population, is it normal or not, so that later you might need this information to answer the question. Okay, so let's have a look for part number 2. They are asking why it is not necessary to assume the daily amount of sunshine is normally distributed. Okay, so why we don't need to assume that the population is normal? Right, so what is the reason? Okay, the reason is because of what? The sample size is large. Because when the sample size is large enough, you apply the central limit theorem, right? So your sampling, the sample mean will be normally distributed without or maybe regardless, okay, to the population distribution. Okay, so you can write as this, okay, as the sample size is large, okay, so which is 300 days. Okay, and then according to central limit theorem, the sample mean is approximately normal distributed. Okay, when n is large, regardless to the distribution of the population. Okay, so because the sample size is large, and then according to the central limit theorem, right, as long as your sample size is large, then your sample mean will be normal, regardless whether the population is normal or not. So that's why in this example, we no need to assume that the population is normal because the sample size is large already. So automatically by central limit theorem, the sample mean will be normally distributed. Okay, so like what I said, they like to ask us this kind of question quite frequently. I mean, from year to year, I can see they are asking more. All right, so please make sure that again, if you want, you can try to collect all these questions, copy down the solution, and then read it again before you go into the exam hall. All right. Okay, so this is what I have for example 9. Okay, so we can continue for the next one. Maybe for the next one, you go for example 10. Okay, so again, example 10, it is another sampling from a non-normal continuous population. Okay, so here they give you a function. So what is the function about? They are talking about the time, x in minutes. So when you talk about times again, it is uncountable. Therefore, it belongs to continuous random variable. All right, so the function is given like this, and then this is a graph that it show you. Okay, so first they want to find the mean and also the variance of x. Okay, so how to find the mean and also the variance of x? So this one it involve the knowledge in chapter 3 again. Okay, so if I look at my graph here, since this is a rectangle, right, and it is symmetry in the range that we consider from 0 until 9, therefore I will know that the mean save time, the mean is the middle. It's in the middle between 0 until 9. So where's the middle for the mean? 4.5. If you want the integration to get the mean, also can, up to you. But we actually learn one easy concept, right? Okay, so when you're having a symmetric graph in a certain range, then the mean will be the midpoint of the range. So the midpoint for 0 until 9 is 4.5, sorry. Okay, so this is the mean. And you want to calculate the variance also. So to calculate the variance, you need to do the integration for ex squared. So if you already forget how to do all this, go chapter 3 and revise it again. Alright, so integrate from 0 until 9, multiply the x squared with the function. So our function is 1 over 9 here. Okay, and then after that, you do the integration. So 1 over 9, you are having x power 3 over 3. That substitute 9 and 0. Then if you didn't do any careless mistake, you're able to get the answer, which is 27. But again, ex squared is not your variance, right? So how can we get the variance? To get the variance, the formula should be ex squared minus the mean squared. Alright, so ex squared minus the mean square means that you are having 27 minus 4.5 squared, and your variance is 6.75. Okay, so please take note that ex means the expected value of x. So indirectly, it also means that this is the population mean. Okay, and then the variance also here, this one is actually the population variance. Okay, all right. So now, first part, they ask you to calculate the population mean and variance. Then for the second part, find the probability that the mean time, okay, highlight the keyword here, mean time. So again, this question talk about the sample mean because you see the keyword mean time here. So the mean time, he has to wait on the random sample 75 occasions. So the 75 is the n, is less than 5 minutes. So that means what? They want you to calculate the probability for sample mean time, right? So it is normally distributed. How I know that it is normally distributed? Because if you look at the n, the sample size is large. So by central limit theorem, the sample mean is normally distributed. Okay, so what is the value for the sample mean of the sample mean? So it is the same as the population mean, which is 4.5. Okay, what is the value for the variance of sample mean? So the variance of sample mean is you take the population variance 6.75 divided by 75, and therefore you can get the answer. Answer here should be 0.09. Okay, all right. So you see the way that we do the calculation for the probability is still exactly the same, like what we done in the previous video. Just that now you need to know what happened to the population. Is it normal or not normal? Okay, then they want you to calculate the probability that the mean time is less than 5 minutes. Okay, so again, you do the same thing because it is normally distributed, change it become Z. Okay, so you standardize it, change it become Z, and find out the probability by using a normal table. If you didn't do any careless mistake, you should get 0.9522. Okay, so please complete the step here and see whether you're able to get the answer correctly or not. Okay, all right, so this is another example for the sample mean that is from non-normal distribution for the population. Okay, so if you have no problem, let's continue to example 11. So example 11 is very much similar to example 10. Okay, so again, you can see that they give you a continuous random variable and they give the function. So this one, they didn't give you any graph anymore. So this is the function that you have. Okay, so that means this is your population. Okay, so this whole thing is your population. First, they want you to find the mean and variance for this distribution. Okay, so again, I'm not going to show you the detail anymore. Please complete this example yourself. So for EX, the answer should be 2 over 3. Then after that, you can try to get the EX square. the answer should be 1 over 2. And after that, when you try to get the variance, the answer should be 1 over 18. So all the values here are the values for population. So you're having the population mean, you're having the population variance. Okay. Then after that, they take 100 observation is taken from this distribution and the mean x bar. So this is a sample mean and the keyword is found. So calculate this probability. Okay, so again, I think it is quite straightforward now. Your n is equals to 100, which is large. Therefore, by central limit theorem, regardless to the population, the shape of the population, your sample mean is distributed. Okay, so you can carry out all the detailed steps that I showed you before. The answer for this one should be 0.7143. Okay, all right. So this is what we have for all the 3 examples that we discussed now. Is actually belongs to the second case in our summary. Okay, so all the 3 examples that we discussed so far is this second case. Our population is continuous. Okay, but they are not normal. All right. Okay, so in the next video, we are going to cover the next 2 cases where population are discrete random variable and they might come out from binomial or Poisson. And then how are we going to solve this kind of question, okay, for the sample mean from a discrete population. All right, so I will stop here for this video. Okay, and then we'll continue the discussion in the next one, in the next video.